Hey there, Physics 11Hers. Just want to quick make a little video here about worksheet 1. You did 1 and 2 for homework. You can check out the solutions. Um, I want to talk a little bit about the further questions, which I'm not going to assign at this point, but they are important. You got to be careful about the direction of impulse here. Number 2, a 2 kilogram block is sliding to the left across a frictionless surface at a velocity of 15 meters per second. A force of 4 newtons pushes on the right side of the block for 10 seconds. Determine how fast and in what direction the block is moving after the force is applied. Draw a picture to help. So you got to watch out for that. It's sliding to the left, the block, right? So that means its velocity is to the left, and the force pushes on the right side of the block. So that would be a force on that side. That force would act to speed up the block, would give it an impulse in the negative direction. So check out the solution for that. Number 4 is actually a really interesting one. This is a hard one to do if we weren't, not being in class together. But it's a baseball has a mass of 141.45 kilograms. A fastball pitches around 40 meters per second. Typical line drive leaves the bat at 49 meters per second. According to research, the average time of contact between the ball and the bat is about 0.7 milliseconds. So what is the average force applied by the bat? Now, if you just jump into this problem without drawing a picture, which I'm going to do here, you'd say, okay, F times T equals M delta V. So force is going to be M delta V over the time of contact. All right, so force, the mass of this ball is 0.145 kilograms. The change of velocity, obviously that's 9 meters per second. And the time of contact is 0.7 milliseconds, which is 10 to the negative third seconds. Cool, 40 meters per second to 49 meters per second. Yeah, it only changed the velocity by 9 meters per second. That's false. I need like the Dwight meme here saying that is false, false. That is false. The change of velocity is not 9 meters per second. And what is it? Well, it's actually 89 meters per second, the change of velocity. And this is why it's important to draw a picture. All right. So you're a batter, right? Let's, who is it? Who plays softball in this class? All right. I'm not sure if anybody does. But here's the pitch coming in, right? Man, I'd hate to try to hit a pitch from Maddie Tallman, other class, but man, that thing's flying in there. Be embarrassing. It's coming in at 40 meters per second, right? But then it leaves the bat at 49 meters per second, right? So the person swung, and that huge ball is flying now, right? So there it goes, 49 meters per second. And you can see the initial velocity is positive the way I drew it, right? The final velocity is negative the way I drew it. So actually, when you do M delta V here, right, the change in velocity here, delta V, actually, let me not make an equal sign there. Let me just put a delta V off to the side here. The change in velocity, V final minus V initial, well, V final is negative 49. V initial was 40, so negative 49 minus 40 is negative 89 meters per second. So the velocity of the ball changes by negative 89 meters per second, which is quite a bit bigger than 9, right? So when we put it in here, negative 89 meters per second, yeah, the negative sign is important because actually that's going to tell us that the force acting on the ball was negative. See, the way I drew my problem initially with the ball moving in the positive direction, that set up everything, right? That set up the direction of the force. Oh, I forgot to put focus lock on here. Just noticed that. Looked up at my camera for a second. There we go. The way I drew it initially set up this whole problem, right? Plus 40 this way, negative 49 that way. Delta V is actually negative 89. Therefore, it must have been a negative force. The force from the bat was in the negative direction. And we can go through and plug it out, and we'll get that answer that's in the solutions, I hope. I'm just going to do it right now. I don't have the solutions in front of me. 0.145 times negative 89 divided by 0.7 times 10 to the negative third. Yeah, you get negative 18,000 newtons, the force. And I think it said the average force, right? So if it said the magnitude of the force, you could drop that negative sign. Now, part B asks us, is the force of the bat constant the whole time? And the answer is no. I'll post a video in YouTube, yet another one, from the Baseball Bat Research Institute. I'm not kidding, it's a real thing. Where they shoot high-speed video of baseballs hitting bats, and they test baseball bats, and it's really pretty cool. But what you see actually is when the ball, like say this is the front surface of the bat right here, when the ball hits that, it actually gets deformed. It actually like compresses on the front of the bat as it hits it, and then it springs off the bat. It's pretty wild. It gets super deformed, the baseball, when it hits. So actually, anytime there's a force being applied, versus time, right? Force versus time. When it first makes contact, it's a weak force, and then once it gets maximally compressed, right? It acts kind of like a spring. The more you compress it, the more the force, right? So the ball hits, gets compressed, it's got a bunch of force on it, and then as it rebounds, that force decreases. All right, so the force versus time looks kind of like this. And it really looks like that all the time when objects collide. Turns out the area under this graph is our impulse, J. All right, which brings us to the next page of the worksheet, right? Turns out if you are given a force versus time graph, the area under that graph is the impulse or change in momentum. So this is a very common thing to have to do in physics, especially AP Physics C, where we're given some sort of force versus time graph and we have to figure out the change in velocity, right? So on number 5, we are given this force versus time graph, 3, 6, 2, 4, 1, 2. All right, this is force in newtons versus time in seconds. So it's a constant force of 3 newtons applied to an object for 6 seconds. So impulse, J, is going to be base times height, 6 seconds times 3 newtons. That's an impulse of 18 newton seconds. All right, so then if we want to figure out the max speed of the object, we take that 18 newton seconds and set it equal to the mass times change in velocity, m delta v. All right, so 18 equals 1 kilogram times delta v. The change in velocity of this object is going to be plus 18 meters per second. So if it starts from rest, it's going to reach a speed of 18 meters per second. All right, so we can find the area under the curve. For the next one, it kind of approximates that curved, this is number 6, it kind of approximates that curved shape on the force versus time. Not really, but it shows it peaking and then decreasing. So again, it's 6 seconds and a peak of, in this case, 4 newtons. And we can go from there. So the area under the curve gives us the impulse. This is 1/2 of base times height, 6 times 4, 1/2 of 24. The impulse is 12 newton seconds. Now, it says it's a head-on collision between 2 objects, right? All right. So when 2 objects collide head-on, they apply an equal and opposite force to one another. It turns out, so if we look at the object on the left, right, it's going to get hit with a negative force, hit to the left, right? Its impulse is going to be, because the force is negative, its impulse is going to be negative. The one on the right gets hit by the incoming ball to push it to the right in the positive direction. So its impulse is going to be positive. So when they contact, they both experience this force, but really the graph for the one on the right, it's positive. The graph for the one on the left, the force is actually in the negative direction, right? Because it's pushing to the left, but they're the equal magnitude, opposite directions of the force. So this ball's impulse is going to be positive 12 newton seconds. This one impulse is going to be negative 12 newton seconds in that collision when they hit. So the change in momentum of each of them must be the same amount, but one of them gains 12, one of them loses 12, so to speak. One of them gets positive 12 units of momentum, the other one gets negative 12 units of momentum. The total momentum of the system is constant. That's important. So because they experience an equal and opposite force when they hit, whatever momentum one gains, the other loses. Whatever the one loses, the other gains, so to speak. All right, so that's important for the next worksheet on collisions. All right, the Regents doesn't get too much into that whole concept. That's why I didn't assign this part of the worksheet. The area under the curves is important. We will talk about that a little more when I give you a Regents practice worksheet. I gotta sit down this weekend and set up next week's assignments. All right. But anyway, just wanted a quick talk about those couple questions. Take a look at the solutions for those. You are semi-responsible for them, but not totally. All right, we're going to move on to collisions. Everybody have a great weekend. I'll talk to you later.